Camera's live.
We're live.
We're live. Good morning, everybody. Happy May. It is now May. We last left you in April. So for day 3, what we're going to do is look at the electrical system, wire up your robot, talk a little bit about electrical faults, types of wiring, and things like that for you. We're also decided that today we're going to review the software setup and get everybody ready with a sample project for Thursday's training, which will be mostly programming the robot and making the robot move going forward. So the core today, oh, we already have a Q question. You can answer that. So that we can go. All right. So if we take a look at the electrical system on the robot consists of all the parts of the robot, okay, that are required to activate the moving parts of the robot. This will be things such as the DC motors and the servo motors, okay, and as well to control any input-output on the controller itself. Additionally, this system is going to include the sensors, which your robot needs to navigate the environment that it's in and to perform any of the tasks in an intelligent manner. All right. The first part of the electrical system are the motors. Generally, right now in world scales, there are 2 types of motors. There's a DC motor and a servo motor. So your DC motors are the heavier motors. The large motors is a picture of the Maverick motor there so that you can see it. Just remember that by default, the DC motors do not have any feedback mechanism. So they'll either spin either in forward counterclockwise or reverse counterclockwise. Okay. Because by default, the DC motor doesn't have any feedback mechanism, it's very, very difficult to look at the state of the motor. This is overcome because the Maverick motor has a separate encoder attached to the back of it, okay? So the encoder is built in. You're also going to get the required encoder cable, so you do not have to increase the length of the encoder cable or change the encoder cable, you know, unless you're going to wire the robot a different way or move your motors. Basically, your cable lengths that are included in your collection are designed because a robot generally, if you look at any of the past competitor information documents, needs to be 600 by 600 by 600 millimeters. Okay, so for those of us who still are old and work in inches, 18 by 18 by 18. So we make all the cable lengths so that you can get successfully and mount anything around that size frame of the robot. Okay. So those encoders are there. They're going to provide feedback back to the controller. And this is generally in simple terms in the form of a tick or a count per revolution. Right? Your servo motors are small DC motors. They have a potentiometer in them. Okay. And as the shaft turns, the resistance changes. There's an explanation there. This will allow the exact positioning of a servo motor. Generally with a standard servo motor, this is within a range of about 180 degrees. We'll talk a little bit more about our servo motors and the default standard range because they are programmable and they're set a certain way. So we'll get into that in a second. The servos are usually controlled by specifying a position, and this is done using something called pulse width modulation. So a PWM signal is used, and this is just a simple square sine wave that varies its wave for width control. All right. So a quick little explanation of the 2 types of motors that are included. We will talk a little bit about the multi-mode servo. So the Studica multi-mode servo. I don't know if James is ready to program one. Has he got everything ready? I'm going to put the pressure on him. As we go forward to get everything together, and we'll talk about it. So you're going to need a servo programmer and a couple of other things. Okay. So the multi-mode servo is now included. This servo in one servo motor will allow for both continuous and standard operation of the motor. All right. In continuous mode, the servo will spin proportionally based upon the input, the PWM signal, either in the counterclockwise or clockwise direction. The maximum speed of this motor is 50 revolutions per minute. In standard mode, which is the default mode out of the box, the servo will act like a regular servo, but it has a range of 300 degrees. So what it will do when you center the servo in the center position, okay, it's going to have a range between 150 degrees clockwise and 150 degrees counterclockwise, right? So you can decide what range that you require based upon what you are designing and building. There is a supplied programmer, and with that programmer, you can change the state of the servo. So using the programmer, you can change the state of the servo from the default range to a continuous range, all right? You can also try to decrease or increase the range of the -150 to +150 as well, okay? Servo uses the same signal, but when you are in continuous mode, basically the potentiometer is ignored, and therefore you do not have position control, okay? So when you are in that mode, and oh, I just got a spelling mistake that didn't get picked up on spell check. So in this mode, the PWM signal is used to simply control the speed of the servo itself, all right? So, yeah, we'll demo it and make you work a little bit harder today if you can power everything up. Okay, so to program the servo, you're going to use the servo programmer. There's a picture of it here. We'll get everything powered up and then we'll go through it. It's pretty simple. You can decide how you want to do it. So this just is the short form. On the online docs, there will be the long form of this, which will take you through it in a little bit more detailed steps when you're going to do it. So you can either set the servo to standard mode, which is the default, or continuous mode, all right? You are going to need to connect the battery up and power the programmer, okay? So the programmer itself can come with an external separate battery pack, so you can use it separately. You can also use this programmer to test your servos. So you can go into test servo mode, just using the programmer to make the servos move, to test them, to make sure they're not damaged and so on, all right? Or what you can do is you can do what James is doing now, is he usually keeps his servo programmer, okay, attached to his robot at all times, and then he can just power that through the servo power block, okay, and he can power his servos that way. So he'll just go over a couple of things. We'll zoom in on programming that servo if you haven't done it before, and testing the servo to make the servo move. I got a question, so I'll look at that. Oh, it's a thank you, James.
Okay, stop sharing.
All right, so I'm going to stop sharing that screen, and we'll go back.
Okay, so to program the servo, by default, it is in standard mode. So we're going to start in the standard mode. To start off with the programmer, let's show what I have. So I use the power block here, so I'm going to power the servo programmer and the servo with the correct 6-volt voltage for it. I have it set to standard mode, which is the switch here at the top is set to S, which is for standard. Then you'll see there's 4 buttons here. There's L, P, R, and S. We're going to hold down the P button, which is the program, for 5 seconds. All right, that's solid and good to go, program. So now if I hit S, which puts it into test mode, you can now see that the motor is rotating between the 0 and 300 degrees, or plus or minus 150. If I hit S one more time, now we're in manual mode. So I can hit the L button, which sends it all the way in the minus direction. I can hit R, which sends it all the way in the positive direction, well, clockwise direction. If I hit P, that's the neutral position right in the middle, so you're 0. And this is an easy way to test the range of your servo motor in standard mode. So now I'm going to put it into continuous mode. So I'm going to put the switch over to C. I'm going to repower the device. Oh, that was the servo. Okay. Now I have to hit program again to put it into continuous mode. So I'm going to hold down P.
For how long? 5 seconds. I was going to give him a test.
And now I'm good to go. So if I hit in the sweep mode. So in this mode, it doesn't do a continuous rotation in the first S. It just goes one full rotation each way. If I hit S again. So now we're in manual mode. When I push P, this is for stop. If I push R, it's going to continuously rotate in that direction. If I hit P, it will stop. If I hit L, it will rotate in the other direction. Do note that this is rotating at full speed. It is not proportional. You can only get it proportional when you actually program it on the Vmx. And that's how to program the servo. Pretty simple.
Where's my screen? There we go. All right. So, you got to take a little bit of practice at that. The short form, like I said, is on the slide. All right. You can see on the slide a close up of the continuous and the standard switch up here at the top. Okay. The power is over here and the 3 buttons to control are on this side. All right. There is a little bit of a short form down on the bottom right-hand side, okay? Just remember that when you're switching from standard mode to continuous mode to change the programming, you'll notice that he unplugged it to unpower and plugged it in again to power up the servo, all right? So that you can see that as you go through. The docs page will give you a little bit more of a detailed description on how to go through step by step and do that. And I think what we're going to do in the next couple of weeks is we're actually going to create just a dedicated 10-minute video on programming the smart servo. We've got a guy here named Armand who's going to do some videos for us, and then we'll add that to the documentation as well. But it's pretty straightforward. So just remember that you can use the same servo now and you can switch it back and forth. All right. Overall, the control system that we're going to wire up and look today basically has the 2 main components. Okay, remember that you have the Vmx controller, all right, which is the smaller object in the picture here, and then we have the Titan motor driver and power distribution board. Okay, this system that you're going to use is also going to control or use the servo power block. All right, it'll have various sensors and modules such as the ADC module, okay, that we use for the I2C, in our case, mostly for the Cobra line sensor, all right? In generally, that Titan controller is going to provide you with a little bit of ability to connect certain things. So you can put the 4 DC motors and encoders on. You can put servo motors on, digital devices, analog devices, I2C, UART, etc. You can look through the documentation and see, what you can do with it, how you can reconfigure the I/O and use the I/O on the Vmx itself. Okay. The Vmx controller also now integrates the NavX technology that we've developed, which is a self-calibrating inertial measurement unit, IMU, with attitude, heading, and reference system. Okay. So that now has built into it 6 sensors. These are going to measure the inertial motion. It's got 3 accelerometers measuring acceleration, okay, and 3 gyroscopes measuring rotational speed. So that is now all integrated inside of the Vmx controller itself. For those of you that had used the WorldSkills robot in the past, it was a separate unit that had to be plugged in. It's now there, it's all integrated together. However, this does, and we discussed this briefly last week, you have to understand how you're going to mount that Vmx controller on the robot, okay, because of the default yaw of the IMU. So we will discuss that, and you'll see that when we're going to wire up the robot and mount the robot going forward. So that's just a brief description of the control system. For those of you that are new and this is your first training, if you can go back to our YouTube channel, to some of the previous training that we've done, we break out the control system piece by piece by piece by each sensor. And then for either Java or C++, we did a simple example on how to program for each sensor, okay, going forward. And we had used a little training block, training unit that we had put together for that. So that'll be on the YouTube channel, and that'll be on some previous sessions from was the summer of last year or the fall, I believe. Okay. I wanted to talk a little bit about the Vmx, and I wanted to talk about the Vmx OS image. Okay, so the Vmx OS image that's on there, the operating system contains a specifically built version of the Raspbian Buster that will run on the Raspberry Pi. So while our Vmx controller is integrated with the Raspberry Pi, and it has a Raspberry Pi 4B there, okay, that is a specifically locked down OS image, okay? So you can't mess around in it and try to do different things because you will corrupt the image and then the other functionality will not work, right? You can download the image, so this is also on our documentation site. So if you run into the fact that you've corrupted the image or you've decided you want to mess around with it and play with it, you will be required to reflash that OS image. Okay, so everything that we do in our training is based upon the default software and the default OS image, right? So if you start changing that, then the things that we show you are not going to work correctly. Right? You can do that. You've got to flash that to an SD card, and this is just a cut from our website that the recommended software to do that is Etcher. So on the docs page, if you have to reflash, the download link is there, okay? And the instructions are there for you to be able to do that. So I just wanted to bring that up on that OS image because people try to do certain things and it's not going to work out. Okay. We are going to talk about the connectors and the electrical interconnects. So it's a topic worth discussing since, you know, sooner or later, you may want to rewire your robot, make a wire longer or shorter, create custom cabling for your robot, okay? We use two general common connectors here on your robot, okay, in the electrical system. So we use the Anderson power poles that you can see in the top picture, and we use either 4-pin or 3-pin or single-pin male to female DuPont connectors, okay, to wire things up. So we were going to talk a little bit about how to create these wires and put them together. For the DC motors and the battery, these connectors are fairly heavy duty because they have to transmit a significant amount of current, okay? They also need a secure connection. So driving your motors and your batteries, supplying power to your system, are probably a couple of the most critical things that you have on your robot. So these require a good, secure connection that is not going to disconnect when the robot moves, okay? Your motors and batteries that we supply in your collection use Anderson power pole connectors. They're a great connector. It provides a stable connection that's fairly simple to connect and disconnect, and we're going to talk about it. They're also color coded to avoid connecting the cables in the incorrect sequence. Right? So both oh, sorry about that. Okay, so you can use those to connect. There's a couple of other connectors that the controller uses. You have encoder cables now included on your motors. These are simple DuPont female header row on one side and a female JST-XH cable on the other, right? All of this stuff is documented on the website so that you can see it. The connectors for the servo motors, they use a 3-color wild cable that are a DuPont connector. These supply both power as well as unidirectional signal to the servo motor. So those are the 2 main types of cables. We will talk and show you a little bit more, but just remember that for the DC motors and the battery, we are going to use the power pole connectors, right? There are also various connectors for various sensors that are going to be there. All right, so the IR sensor uses a 3-pin JST connector on the servo side and a single-pin DuPont connector on the other side. Okay, little note there. You do have JST-SW to JST-GH cable, for instance, to connect an I2C cable.
JST-SH.
JST-SH. Yeah. It was late when I was doing this. So JST-SH. You have JST-GH to DuPont cables. You have an ultrasonic sensor cable. Okay. You have some female-to-female DuPont cables that you can use for the Cobra line sensor, or you can create your own. You'll have a CAN cable for the CAN bus, and then you'll have the camera module with the cables. This includes the ribbon cable to mount the camera and the HDMI cable to run from the module to the camera itself, right? So out of the box, you should be able to cable everything that's included to get you going to build a basic robot in the various cable kits that come with the collection, right? Overall, when you're wiring, as I just said, most of you are going to use the pre-supplied, pre-made cables to get started, especially for the power system. You may have to create your own cables, and you can create those by purchasing raw connectors and cables separately, okay, and then using a correct crimper to mount the connectors to the ends of the required cable lengths. All right. Cable management is appropriate here, and you want to make sure that your cables are not too long, that your cables don't bind, okay, and that you are also using the appropriate gauge of wire so that you can see it. If you haven't done a lot of this before, our online docs, we add to them all the time. I just did a document a couple of days ago that talks about different wire gauge lengths and what you use wire for. And we will show you some crimping today. And then we're going to take everything that we do and put that in step by step with pictures for you if you haven't done it before. All right. We talk a little bit about strain relief a lot of times when we're wiring robots. So this is important. I will let you read through that. I won't read the whole thing for strain relief, okay? You just want to make sure that generally there's a bit of slack in the wires so that if something moves, okay, that wire is not continuously bending because it can break and there's no relief on it going forward, all right? Okay. So we'll talk about crimping. James is going to show you some examples because he's much more adept at this than I am. And he gets a lot more practice. We have a power pole crimping tool that you can get that works well for crimps, usually used for 12 AWG and 14 AWG wire with our power pole connectors, okay? And he'll take you through a little bit of a sample. This is the way that I do it. I use a 45A crimp, then a 38 die, and I crimp again. So if you see my document that I wrote, that's the way I do it. Everybody has their own little way, okay? And then there's a couple of other little crimping tools that we can use if you wish to make, for instance, your own PWM cables, okay? And you can, the presentation when we upload it, these will have little hot links in them that'll show you how to get those cables and look at those cables as you go forward, all right? Okay, so I'm gonna stop sharing and we're gonna get up here and show you a little crimping as you go through.
So we have a bunch of university co-op students in, and they were assembling our trading platform. And when they tried to make their own cables, they didn't do so well. As you can see here, the crimp was terrible because they stripped too much wire or they didn't crimp properly, and it makes the connection very loose and not good.
So we thought you'd show you a sample. I found this on the table this morning, and it's very, very simple. As you can see, we can move that. It's not secure, and that especially here at the end of this, I have exposed cable out the back that can fray and cause issue and cause shorts on that power pole connection. All right. So we got our little master cable kit here that we have, and we keep everything well organized with our shrink wrap and so on. So we just put this stuff together for most commonly used connectors, and we're just going to go over, and James will crimp a cable for you.
Yeah. So right here I have 12 gauge silicon wire, so it's flexible, which is very good when wiring through a robot, as you can bend it around corners as such. Some other terms for this wire would be like stranded wire. So you would look at different wire strippers. This one's too small, as it does not do 12 gauge wire. So for the thicker wires, I like to use this type of stripper, which you just have to do that and it'll auto strip for you. You don't want to strip too far, so you can set how far you want it to strip on your wire. That would be way too far. So the default is normally okay. So you can see I only strip about a centimeter off of the wire. And do a little twist to make sure the wires are all together, as it's a stranded, not solid wire. Then I'll take a 45 amp contact, and then I have my power pole strippers, connector, which is right here for the crimp. There are 3 slots in the power pole crimp. There is a 15 amp, a 30 amp, and then a 45 amp slot. As we're using a 45 amp crimp, we put it in the 45 amp slot. So I'm going to slide it into the slot first. It seems our university co-op students damaged the crimp. It won't go in. Let me try and adjust it. Here, just hold on. I'll go get Derek to grab another one. You go grab another one.
I will do that. Okay.
Derek's gone to go grab another crimper, as the back here has been dislodged, or they jammed something inside of it. I can't really see. Let's see, can I loosen it?
Did they take the die off the back?
I don't know. Yeah, let's see if this one works.
Oh yeah.
But yeah, the crimp won't go in.
over torqued it.
There we go. So if we look, the crimp is now inside the base there. So I can take the wire. I don't want to get the insulation inside the crimp, otherwise it won't crimp properly. So when you put it in, make sure not to get the insulation. Good tight crimp. I like to hold for a few seconds just to make sure that it's good. Let go. Good to go. Now you'll take the housing. It's a bit difficult to see on the camera, but there's a specific way that this goes in. I'm pretty sure Derek will post a document or a picture that shows the best way to put it in. But you'll slide it in, and then you'll hear an audible click, which tells you that it is connected. I'm not sure if you'll hear it. So when you hear that click, that means that the cable is in, the crimp is inside the connector properly, and you will be able to mate it to another connector easily.
You gotta move forward like you told me last week.
All right, that's nice and tight. Let's do another one just to show. So take the strippers, strip off about 1 centimeter. Tighten strippers. About 1 centimeter. Twist it. Stick it in there. Hold for a few seconds. Let go. Good to go. You also don't want to strip too much wire, because then the wire will protrude into the smart contact area, which would cause issues when trying to insert it into the contact or when you're trying to mate the two contacts together. Slide it in. Then you're going to wait for an audible click. There's the click that tells me it's good to go. And I can now create an infinite loop. Okay. Very simple connector here.
Yeah, I've got a document that we'll put up that breaks this out step by step by step. There's a couple of different ways that people do this. Some people double crimp the connector. And a lot of that depends if you're using 12 AWG or if you're using 14 AWG.
So just to show the difference between a good crimp and a bad crimp, if we look at this crimp and I try and move it, you can see how tight that is, and there's no sway or pull or anything. Meanwhile, if you look at what our university co-ops did, you can see how much play there is and how it's not good or connected at all.
And that's just because they left too much wire out when they were stripping the wire, okay? So when you're doing a power pole, generally about 1 centimeter is the most important part when you're gonna do it. All right? You wanna do a PWM now?
No, those are two, you can't see that.
Yeah, okay. All right. So we just want, what's that?
Other one.
If you want, yeah, go ahead. We'll do a couple of different ones, and like I said, I've broken these all out in step by step. Okay.
So in your kit, it's also a control panel. They come with these spade connectors, which are used just to slide on to your the contacts of the switches on the control panel. So another good tool to have is the crimp for that. We use the specific one, which gives us color coded, makes it much easier for us. So we know if we have a yellow crimp, we'll use yellow one. So I'm just going to demonstrate that one.
This is mostly for Derek, who still doesn't understand after 35 years wire gauges properly. So yeah, we found a crimp that was color coded, It makes it nice and simple. So whether we're going to use a yellow, blue, or red terminal, we just match the colors.
So these spade connectors are really easy. Just strip off some wire, stick it through the hole. You want to get enough cable that the cable goes through where the contact area is, and then you want full insulation where the just plastic area is. So I'm going to stick the cable in. And then this is yellow, so I'm going to use the yellow contact area of the crimp. These crimps have a very strong gripping force, so normally it takes 2 hands to do. Hold for a few seconds, let go. And my spade connector is now, as you can see, it's double crimped, which makes it nice and tight. It'll crimp on the electrical side and on the insulation side to make sure it's a nice, strong contact.
Yeah. Okay. All right. So, just so that everybody is aware, if you want to get stuff, we used a tri-crimp crimper. Okay. We have a PWM crimper as well. All right. That you can see. We had a wire stripper, and we keep a wire cutter, right? Angled wire cutter as well. Okay. And then we had our crimper, right, for the female and male spade connectors, right? And we just keep these around, and we got them in our toolboxes all the time. Okay, so we're ready to go, right? So handy tools to have when you're wiring up your robot, rather than just trying to use pliers, okay, to make things connected. We didn't show you how to do the PWM because they're a little bit small. You can get multiple connectors, okay? These are 3-wire with male or female terminals if you want to make your own cables. They're the same thing. You crimp them on the wire, okay? Then you push them into the connector block. So all of this was the short form. I took it out of some documents that I've been writing that go, I think, in chapter 8 of my new robotics curriculum that we will be posting online for everybody on our learning management system. I was just down the hall discussing that with Frank, who showed up for work, which is always nice. And with that system, then chapter 8, as I call it, I think right now, is all electrical connections. So we go over sample tools, sample wiring, wire AWG, types of wire, because James was using this silicone coated wire in this case, which is a nice wire, but of course it can be difficult to get. All right. And it can be a little bit expensive sometimes. All right. And you'll notice I call silicone wire noodle wire because you can hold on to it like noodles. Okay. As opposed to non-silicone wire like this one, which tends to be a little firmer and a little stiffer. Okay. As you go forward. The motor cables are actually a silicone type wire that we use on your motors, just to give them a little bit more flexibility so that they don't bend under wire or strain relief. All right. Okay, I got one more little talk to do here, or a couple of different things. So what I'll do is I'll share my screen again so that you've got that. All right. And poof, like I said, these are the short forms because we didn't want to do a whole 4 hours on just wiring things. It is important on your robot to have ESD and electrical protection, okay? We want to control power spikes, okay? We do not want components to disconnect and reconnect, especially while the robot is moving. I tell the story of, we did a practice competition in China a couple of years ago, and there was a robot that kept stopping and starting on the court, and there was a lot of, complaints going on about certain things, and it just turned out to be something simple. The bottom of the robot had a short in it, and every time the robot started and stopped, it wiggled a bit, and the short caused the whole electrical system to reboot. and then it would work fine for a while, right? So, you know, between the hour of people arguing about Wi-Fi connections and this and that, it just turned out to be a simple, loose, strained wire. That's it. So there's a couple of ways here. I just talk about connecting components. Make sure that all your motors and sensors are connected to the controllers. Then connect the power switch or the battery to the controller via the power switch. Don't plug it in directly. All right. And then use the power switch to power on everything. So, and then I tell you to turn things off in the reverse order. I understand that not everybody does this every single time, but for every piece of electrical equipment that I own, my wife would say this because I have rules at home. This is the way you turn something on and this is the way you turn it off. Okay, and you will plug everything into the power bar first and then turn the power bar on and then turn the device on. So, you know, a lot of different things so that we don't get electrical power problems. All right, cable management. So when you're building your world-scaled robot, it's important that you think about cable management. You want to use your cables that are at least long enough to cover all robot mechanisms when it's fully extended. You will see on the robot that James has put together that he has certain cable management techniques that he used. It looks clean, it looks crisp, okay, because otherwise I give him a hard time about it. Slack cables can get caught between robot parts. They can get pinched. They can cause a short circuit failure. So it's very, very important to route your cables so that they stay out of the way of things. It's also very important for you to route your cables so that it's easy for you to troubleshoot any problems. So you want to be able to get access to them and see what's causing a short or see what's a problem. And you have to remember that if you have to replace a cable, that you're really going to need to be careful there. You know, little things like cuts in the coating on the side of an encoder cable can cause problems. So, you know, make sure that rather than have to replace the whole motor, you can simply replace the encoder cable, okay, as an example. All right. And I think this is the last one I'm going to do before we take a break and we do things. I'll have to double check troubleshooting your electrical system. So I have a whole troubleshooting list that I put together. So what I had done on this point was I just quickly talked about checking a few things. So you want to check your battery connections, okay? We have blade fuses in your Titan, okay? So there's 20 amp and 10 amp and 5 amp, I think, blade fuses in there. You can check the fuses to make sure they're okay. You can do the tug testing on your cables. So James had shown you how he pulled some cables. So you tug all your cables, you make sure that everything doesn't pull apart and that you don't have any loose cables. And I also talk in here about checking your firmware and your versions. And I'm going to talk a little bit more about checking the firmware and the versions, okay, going forward, okay, and when you should upgrade and when you shouldn't upgrade firmware or software versions on your system, because these can also cause problems. We have had people do version upgrades of software and then their robot stopped. Well, yeah, because all the original library code didn't match that. So, you know, was that caused on your firmware or on your system? Okay. All right. So what we'll do right now is it's 7:50. We've gone 50 minutes or 45 minutes. Let's take a 10-minute break until 8 a.m. Then we're going to talk about the software setup and installation. So we threw this in here so that when we're wiring the electrical system, we can show you how to do the software setup and how it's going to work, okay? And to make sure that everybody has the correct version before we get into programming next week. So we thought we would add this now in case some of you had to, you know, leave early or do certain things, okay? So we'll just take a quick break and we'll see everybody back here at 8 o'clock. Okay, we're back, we're live. Sorry about that. It was not a tuck that showed up. It was a truck that was not supposed to show up till Friday. A lot of moving parts going on here at Studica right now. And of course, most of the people show up at 9 o'clock, not 8 a.m. So we had a little bit of quick work to do. We did want to talk, as I said before the break, about the software setup because you are going to require to have the software set up and to get going. So we thought that we would add it to today so that you have a couple of days to get ready for Thursday, okay? The software setup requires you to use, at this point in time, what we call the offline installer, all right? The reason that we use the offline installer now is that Microsoft, in case any of you have experienced issues with Windows 10 updates or security updates in the last 3 or 4 weeks, has changed a lot of things. So we had an online installer where you could do everything online, but a lot of the links to Microsoft code and things were all changed. They haven't been remapped yet. There's security issues, so that doesn't work. The offline installation files will be located on the USB stick, okay, that was in your collection, this little blue USB stick. There's resources on your USB stick. We find that what a lot of people are doing is they're thinking we just gave you a free USB stick, okay? And they're deleting the files that are on here or overwriting the files that are on here or giving the USB stick away for Christmas or something like that. So remember that the resources are there. So the offline installer is there. Okay, there's 2 files. There's a 64-bit version and there's a 32-bit version, right? If you do not have that USB stick or need to install the software, there is a link, all right? And the link, what we'll do is, it's in my PowerPoint presentation, so that if I actually click on it, it will pop up, and I'll show you that in a minute, okay? And I will post the link inside of the chat when we're gonna get going. So I'm just gonna share my, I am screen sharing right now, so we're gonna get sharing. Well, there I am. So when you get the link, okay, I'll create a new share. What it will do is it will take you to here, okay? So on this side, you'll see that this is the USB contents. We've shared it on the Studica Robotics Resources SharePoint file. So you will have the step files there for your CAD files. You will have the Windows versions, okay? And you'll see that the installers are here. So there's the 32-bit and there's the 64-bit installer, all right? So you just want to, James will go through the installation of this in a second as you go through. All right. Right. A couple of other things. We are using the Wpi Lib Software Installer, okay? And this is because the Wpi Lib provides us some libraries and classes that are pre-done for you and allows you to get started with a robot without having to do code, okay? And WPI has graciously allowed us to share this and use this with you. You can only use version 2020.3.2 for World Skills. You have to remember that WPI Lib is licensed and used for multiple robotics uses around the world, for different competitions, for different learning, for different R&D, okay, all sorts of different things. So while there are 2021 versions, remember that in my last slide, I talked about versions of software and firmware. At this point in time, if you try to run any version except for 2020.3.2, okay, your code will not work. You will get errors. So a lot of people think, oh, I'm gonna upgrade. But the problem when you upgrade one thing is that everything else is written for this version. So this is the version for World Skills. That's why we put it now on the SharePoint site, and that is why it is on your USB stick, okay? So please remember that. I guarantee you that the majority of people will not remember that, and you'll try to upload versions and then your code will not work. Okay. The next part is just a quick thing off of our docs page, okay, about using the VS Code, okay. So you're going to run VS Code as your main IDE. It is a VS Code version for WPI, all right. So when you install the WPI installer, there'll be the separate button there for you to select and download the VS Code. You want to follow these instructions. So even if you have VS Code on your system or already installed locally, okay, this install will create a separate version of VS Code that is designed and built with all the plugins you need for the robotics development, right? So this is the installation instructions that you must follow. This is the short version of that offline installer. So I hope that's clear to everybody. It'll save you a lot of heartache getting set up down the road. Okay. We'll talk a little bit about the Wpi Lib. I did this in one of our previous sessions. Okay. This is the main library program that we use for the robot when using either Java or C++. And that's what we are using here at this point in time is Java or C++. Other languages we are developing, we do have some resources available. They will not be covered in this training, okay, because they're still in development. We have some people who are working on those in beta. But, you know, remember, this is what we've got all the free resources for. The library contains all the code you need for basic robot functions. You're going to see a sample project. It contains a lot of code to make performing your functions easier, such as checking your inputs from the gamepad that's supplied. The library also contains a lot of the many common tasks that the robot needs to do. Okay, it won't program your robot for you, but it's a really good head start to get going. Learning what is included in WPI and learning how to use all of its classes and methods is very, very useful, okay, to you when programming the robot. So we will cover this stuff as we go forward and do it a little bit. All right, I'm going to give this back to James because I think he wants to go over the installation, correct?
Sure.
Do you, or we can?
He's
going to show the docs to go over the installation. That's right. We do not want to reinstall everything right now.
So we look on our docs page, we have the offline installer information. This is found, you can either go to getting started or straight to software setup. I disabled the online instructions because of the linkage error. So in the offline installer, you can find the instructions for that. It's pretty much step by step for you. If you're on Windows, you can follow the Windows instructions. If you're on a Mac, you can follow the Mac instructions. And if you're using Linux, you can follow the Linux instructions. I'm going to show the Windows instructions. It's meant for Windows 10, but if you are using Windows 7, there is a specific version of Net that you must install, and that can be found by clicking on the link here. So you'll find these files inside your USB. Choose the one that's based on your operating system. So if I have a 64-bit, so I'd run the 64-bit exe. There'll be a prompt to ask you, do you want to install it for all users or your current user? That's up to you. All files are installed into a specific folder in your public library. This is because when there's releases for multiple years, it just changes by the date. So when we finally push to 2021, you'll see that there'll be a 2020 version for what we're doing right now. And then when we switch to 2021, there'll be a 2020 version there as well. So you can always go back if you wanted to use old code. So the install is simple. it'll pop up like this. It will install the correct version of the GCC along with Gradle and Java JDK so that everything works together. Don't assume that you have the correct version on your computer, as you may have an older version or a newer version that is not compatible. So you must make sure that these checkboxes are checked so that you get the correct version. For example, the 2020 version of the VS Code uses Java 11. And if you do not have Java 11, it's not going to work. So if you have the current, I think it's Java 15.
Yeah, it's 15.1.
It's not going to work for you because you will get errors. You must have this checked and it will download Java 11. And then the last few ones here should be checked anyways, as this installs your shuffleboard and everything else for you. After that, you'll have to click on the select download VS Code. The download won't work, so if you click on download nothing, you'll get that link error. So what you want to do is click the select existing download, and then you can choose that zip file that is on your USB. Once you choose that, you'll be able to hit execute install, and it will install everything on your computer. So to go over what's installed on your computer, there's a specific version of VS Code, which has all the tool chains and links put together properly so that when you hit build or you hit deploy, everything works and there's no error. There's the specific tool chain for building C++ code, the JDK and JRE that's specific for the targets that we're using. Gradle is used to build for Java and C++. Then there's tools for robotic instances such as the shuffleboard. Then there's the dependencies, which is your OpenCV, the robot libraries and everything to compile your code. And then there's the VS Code extensions so that you can build everything properly using an extension. You don't have to manually go and find stuff and do it. And
right,
that's the simple installation.
Yeah, so the important part here is that if you're already using Java, if you're already using C, if you already have your own development system, okay, great. But all of the dependencies and all of the libraries, okay, they're going to be all over the place. So if you follow the instructions and install this version, everything is set up for you, right? It makes it a lot easier from that programming standpoint. Because we've had some people say, well, I already got Java installed, I'll just skip that. Well, no, because this builds all the dependencies, all the libraries are matched, all the sample code is matched to the directory structure and so on. And the reason you do it is just to make your life easy and simple. It's quick, it's straightforward, does not take very long at all. And even Derek figured it out. So it's pretty simple as we go forward, right? So those are the instructions. If anybody, what I'll do in a minute when we get going on the wiring and James is talking about the wiring, I will post the share into the chat in case you don't have it, where you can get the offline installer stuff, just in case you don't have the USB. And I'll post the link to the docs page as well.
Link to the SharePoint.
Yeah, the link to the SharePoint is there, so it's nice and simple. Yeah, okay. All right. So we're now going to go on and get the robot all wired up, all right, so that you can see it. I'm just going to share my screen again. I got one more massive slide. Okay. So overall on our development here for our robot, this is a simple, basic wiring schematic. All right. We decided we wouldn't give you anything too complex. It's just to show the various connections that are available for you. But James will go over it from that standpoint. But our robot, as you can see, is going to have the Vmx controller, okay? And it will have the Titan quad put together, okay? So we're wiring the CAN to the CAN between the two. We're wiring the power distribution from the Titan, as an example, through the Vmx, okay? There are 4 motors on this robot. There are 3 drive motors, and there is 1 elevator motor, okay? So those will be wired, and they'll be wired into the Titan, okay? You will see that we're using FlexDIO for an ultrasonic distance sensor. We're going to use an analog port for the sharp IR sensor for one sharp IR sensor. Okay. We will use the I2C and the cable that is supplied with the ADC to plug in the Cobra line follower sensor. So this just gives you a rough idea. And then all of the servos will power the servos power module from the Vmx with the supplied cable. Okay. And then we'll power our servos for our just one servo on this robot, right? From the servo power module. And remember that when James was working on his servo power module, that he'd actually plugged the servo programmer in right in through the servo power module, okay? So you have extra inputs and outputs on that so that you can program your servo, okay, you know, right from your servo power module if you want to just quickly plug the servo programmer in. So that is a simple breakdown of the wiring schematic. When you go into the World Skills competition itself, there will be a technical journal sample that we did this year. I believe that we will supply to you. It'll talk about the wiring schematic. I did not talk about labeling wires in here. I was gonna go down and break through labeling your wire samples so that you can match wires back and forth and how to label your wires and so on. I did not delve that deep into it in this training. I didn't get out the wiring done. But there will be some samples in our new curriculum on labeling wires, wiring standards, and so on. Everybody's different. Your instructors are different. Your experts are different. I just encourage people to label their wiring so that they understand where each wire goes. And please make sure that your schematic matches your wiring. So if it says wire A to wire A on your schematic, wire A shouldn't go to wire B on your robot, okay? Because that'll get checked by your experts when you are at World Skills. Okay. All right. So I'm going to stop sharing. We're going to get the robot up here, okay? And we're going to start to talk about wiring the robot up and getting it ready for movement. What?
Can you show it on the big camera?
We can't show it on the big camera, the little camera, you let me know and I'll leave.
I think the small one's good, and we'll switch to.
Okay.
So this is the wiring on the robot, well, where everything mostly plugs into. For mounting the Titan, I just used a 96mm channel with some of the end pieces in it. And you can see these two screws here screw into the end piece through the 96 channel. And then the 96 channel is screwed in from the two channels up here to hold the Titan in place. It's pretty firm. That's not in the CAD, so if you want to just take a screenshot or snap that just so you know how to assemble that or make it up on your own, it's up to you. With the Titan, it's mounted on the back because this gives me a very ease of access to get to wires, unplug them, change them, and it's just a nice place to have it because it's out of the way. So we can see here that on the M2 motor, which is right here, we have the elevator motor plugged in, which is on the side here. The M3 motor is connected to this right front wheel. Sorry, left front, because it's the left of the robot. And then we have the M0, which is here, is connected to the right front motor, or wheel, as you can call it. And then lastly, the M1 is going to be wired through and connected to the back motor. The way I did this was because that's where the motors were closest to on for wiring, which allowed the wires to be a little bit tidy. Normally, I would cut the wires to the exact length and then re-crimp them with the power poles and the deep DuPonts for the encoders. But because I don't want to do that, as we may make other robots in the future, cutting them to the exact length would not be wise. However, if I was making a permanent robot, such for world skills, and I already know the cable length, I will cut them to size. That way, there's no extra cable that's in the way, and I don't have to worry about it. You can also see here that we have the power coming from the battery. This slides through here to here, where I have the battery located in the middle of the robot. That's not shown in the CAD, so I will flip the robot over so that you can have a look. Essentially, the balls came up.
Two of the balls came up.
Essentially, all I did was take the 196 by, I'm sorry, the 192 by 96 flat plate that we include in the kit. I screwed on the battery mounts, which are located there with some 25mm standoffs. And then you can see here and down there where I screwed the plate into the bottom channel. This, it's not screwed over here, like the end here. That's held by the motor, and it's pretty strong in there. That will hold the battery so that. And what's nice is if I bring this here a bit, you can see I can jam my whole hand in there without touching any wires or getting my hand jammed in a motor, which means I can easily place my battery in there and connect it to the battery wire here. So if I was using the control panel, the battery would be going to the control panel, and then the power, this power would be connected there. But I'm not doing that. And then of course, if you have a run after, you can swap your battery for the charged battery, simply just by reaching in there and taking the battery.
So the important part here is battery is probably one of the heaviest parts on the robot. We have to really be careful of the center of gravity, okay, in our design, especially in a 3-wheel drive robot like this, because balance is important. Otherwise, you know, we're going to get tracking, extra weight on one side of the wheel or whatever. Remember that the design is consistent in the distance and that everything's 120 degrees apart, but it's nice and easy to get that battery in and get that battery out. Simple things. If I blew the fuse on the battery and it was inside there and I couldn't get at it, or do a quick battery change, you know, that could be the difference between being able to get a run on competition with the robot or not. So you want to make sure that it's centered, right, and that it is accessible when you do your batteries.
Another thing that you can see here is that I have the servo power block attached right to the side here. That's because if we switch, if I hold the robot up, you can see we have a cable chain. And Derek's just gonna.
You want me to? You want me to zoom in?
No. Oh yeah, you can zoom in.
I can figure out where the zoom is.
It's on the right there. Yeah, just
Put that up.
so if you see, there's the cable chain. And what happens is the servo.
I'm going to turn that down a bit. So James has his hand on the servo power block right there, which we mounted on the side. Okay.
So you see the servo will go from the output up through the cable chain, down the cable chain, and then go to the motor that's in the middle to allow for the cable not to get caught in any mechanism. And of course, the cable chain is not in your kit. However, the cable chain is considered wiring and therefore is allowed to be brought in and is legal for the competition.
So it's just for wire management and ease of use.
Right. Switch to the other camera. So if we look at the top, here we have the Vmx, which I saw some of you were mounted on the top here. I have the Cobra ADC mounted here. It's not attached to the Cobra right now. As you can see, there is the open ports right here, which the Cobra plugs into. One thing to note is because the pins from the headers extend below the board, I use 2 2mm standoffs here underneath the screw points to raise the board up so it's not making contact with the channel. Because if it was making contact with the channel and I were to turn the robot on, I would short this out as the 5-volt rail or 3 point, whatever voltage rail would make contact with ground. And of course that would short. Another thing you can do is put electrical tape on it or 3D print your own case or over it. But I like the standoffs because it just, well, actually not standoffs, spacers, because it will keep it better. And then while we're looking at this, there is a VCC, so a voltage port and a ground port here. That's for you to attach a screw terminal to if you would like to add external power to power a stronger sensor that needs to be powered. But if you're just plugging in the Cobra, you'll be fine. If we look on the Vmx, we have the CAN cable right here, which is then routed down through to the CAN port on the Titan. We have the camera, the top module where the HDMI plugs into. What I did was I measured out some holes on the top of the case, drilled them out, and then tapped them with an M2 screw, well, an M2 thread, which then can be screwed in and screwed tight, which attaches this tight to the lid, which prevents it from flapping or moving. On the left, on this side, I only currently have the servo plugged in, as we have no sensors except the encoders right now on the robot. Right now I'm plugged into port 12, which is PWM0 in your code. And that will allow me to move the servo motor when I send a PWM signal to port 0. You can also see here I have the power cable for the Vmx, which is routed through and connected to the power cable here at the bottom. There's also another power cable right next to it there, which connects to the power for the servo ball. That means that all the power routes through the Titan to the peripherals, and we don't have to worry about the ground loops or anything like that, or the ground's not connecting properly as signal won't work then. It just simplifies it. And that is the simple wiring of the robot.
Yeah, I choose sim.
All right, so Derek wants me to show you. So here is the ADC. The reason why we have the ADC expansion was that there's only 4 analog ports on the Vmx. So that means when you plug in your 2 sharp sensors, you will not be able to read the 4 values from the Cobra sensor. You'll only be able to read 2. So we created the expansion here so that you could read all 4 at the same time, plus have your 2 sharps plugged in and all the sensors will be working. But in order for this to work, it gets plugged in through to the I2C port here. The cable comes connected, comes with the module, so make sure you don't lose this. And there already is libraries for it in the vendor library that we provide for everyone on the VM.
and then just right. And then the only other thing on here is James showed you each motor and each corresponding encoder, okay, is wired through the Titan quad, and you'll see that on the diagram. So the diagram just has one arrow, but remember that you've got your power for your motor and then your encoder for each motor, okay? And you can see clearly the orientation of the encoder cable on each one of these, okay? And it is diagrammed in your documentation as well.
It is also on the Titan.
Yeah, it's on the Titan as well, so that you can see it. It's printed right here so that you make sure that you get each one organized correctly. So it's a pretty simple to wire a basic robot right now. In this case, so we didn't have to chop or cut any wires because we like to take this apart. I think the only one that we actually cut was the CAN cable here, right? To go between the Vmx and the Titan. But then everything else, we just use the zip ties. You'll see to clean it up and to tighten it up so that you can see it. If he turns that on its side, okay, you'll see here, we just tighten those cables up inside the channel to keep them out of the way, and then use the various zip ties to keep everything from moving. If we had to rewire this, very simple, just cut that zip tie and then move it. So we are actually using the way that this robot is designed, the open side of the channel as our channel guide for our channel management, right? And this is what you like to see, nice, clean, and tight. Okay, I think in one of my last presentations, I showed you what I call spaghetti wiring. So spaghetti wiring is like spaghetti code that goes everywhere. It's very hard to follow and very hard to understand, but you can see that, you know, I can follow that cable easily for that servo, and I can see this cable here coming back, all right, from, you said port 12, PWM port 0, right, which is port 12 on the VMX, and then comes in and then goes back out again to the servo, okay? So remember that your ports are still here to control your servos. They come to the servo power module, which gives the power to the servo, and then back out, right? So a nice simple way to do your wiring, okay? All right. So it's pretty straightforward. It's 8:30. What we'll do is we're going to leave the picture of the robot up so that you can see the main connection there when you've got that. I will post that PDF in the chat and the link to the software in the chat. So if you can go through and get your robot wired, let's see what happens to everybody in 30 minutes. I'll post everything up and we'll see if you can get it wired up in 30 minutes. If you're not, you know, we'll give you more time. We got lots of time to get the robot wired up. And then maybe even today we'll get to forward to look at a sample project, or at least to do some testing on the robot. So we'll leave that up and I'll put the links in the chat for you right now. And we will be here if there's any questions as you are wiring your robot.
All right, we're back, everyone. Hopefully you're all wired. One of the things we also wanted to go through today was there were some people that had problems with importing the example projects into their VS Code and then getting those projects to work. I'm going to show an example of getting the example projects and importing them into VS Code and getting them to work for you so that you can see how it's done. So first off, let me find it. Is it working? Or do you think?
What? I will tell you. I see the Studica docs, world skills. Yeah.
All right.
Good to go.
So in our one GitHub location where we have the world skills examples, oh, that's the docs. Let me switch to the example. Here. So in the example projects, we have all the projects that we work through within training for you to see. These projects are really simple. You just find which one you want and you import it into Visual Studio and you'll be able to make it run. So for example, for our elevator that we did a few months ago, we have the C++ and Java version of the program. So go here, this is all the code for it. And then here's all the C++ code for it. So to get it to work for you, you could just go here to the big green button, hit download zip. This will then download the zip to wherever you like. I have it placed here on my desktop. So we can see that we have the code here. So Java, C++, etc., etc. So what we're going to do to show it is here is the VS Code. It's blank. There's nothing in it. What I'm going to do is hit File, Open Folder, and then find that folder and open it. So File, Open Folder. I just need to find the correct folder here. So when I hit File, Open Folder, I can choose a folder to open. So let's do the training platform, which is the other training platform that we work on. Let's do the C++. Just give me a second. I have to disable something, my antivirus, before I open the C++ project. And the reason for this is that if you have antivirus with the C++, when it tries to compile that exe to send to the Vmx, your antivirus will block that, and that will cause it to not work. So I disabled my antivirus. Let's now go here. I've opened up the folder where I'll see all these named folders, and I'll hit select this folder. And you'll see now that this folder will open. When you open the folder, it will auto build. That's part of the extension. As you'll see here, it's now building with Gradle and populating the folders as required. So because we're using Raspbian, right now what it's also doing is it's downloading the Raspberry Pi toolchains and everything else and caching it so that I'll be able to build offline. If you're not connected to the internet, this build will fail. So you always have to remember when you first start build your project, or if you're adding in a new vendor library, you must be connected to the internet in order for it to download and cache these libraries. So it's cached the libraries, and now it's actually building the executables for it to be sent to the robot. So as you can see, I had a build successful. It only took about 1 minute, which is pretty good. Let's have a look to see that the code imported correctly. So source. So we can see here that my subsystem was imported and everything seems to be working. Let's go over one of the issues with C++, and that is sometimes you'll get an IntelliSense error where it won't find any of the libraries. The libraries are there, but it's actually just a VS Code bug. So what you would have to do is you have to exit out all your open windows. Bring the command palette back up. This can be done via Control-Shift-P or hitting F1 on your keyboard. And what you're going to do is you're going to hit this C++ refresh C++ IntelliSense. So when you've done that, do this. It just refreshes the IntelliSense. And then when you go to open your project again, or any file, the links will be there properly. And you won't have any issues of it saying file not found or errors shown by the VS Code. This is only an issue with C++. Java does not have any IntelliSense issues, as it's built in, there's no issue. We can also see our header files here, for example.
Yeah.
Our system file. And that's just an example to show how when you grab a project from the GitHub, for an example, to bring it in, and I'd be simply able to connect to the robot now, and I can run a deploy to the robot. Another thing is if you change the team number for your VMX, you will also have to change your team number for in VS Code so that I can compile and find the right controller to send it to. So if I go to the .wpi lib folder, you'll see there's a preferences JSON. You can see we use 1, 2, 3, 4 as our default. However, if you had a different one, what you want to do is run a command called set team number. I already find it right here. So I can choose different team number. Let's say I wanted to be team 4321. Hit enter, and they would change that. The reason why we have to change it through here and not manually through there is that there's a lot of background areas that it changes as well. So we'll run a build too before we do anything to make sure that it builds with that new team number. Right, it'll take 7 seconds, not bad. So now if we look here, we have team number 4321. And we'll be able to, when we deploy to the VMX, it will connect to the correct IP address and everything will be deployed correctly. So now if I wanted to open up the Java version of the same code, what I could do is File, Open Folder. I'm in the trading platform already, so let's choose the Java one and then hit Select Folder. And you'll see that it will now open the Java version and it will execute the build where it will populate everything that's required. And there you go. Everything is now cached and built. So if we look here, we can find the Java version of project. So between now and Thursday, we will be posting the example project for the training robot right here. Hopefully you'll be able to download it and bring it into your VS Code. I will be going from scratch how to program that in VS Code. So if you want to do it that way, you can do it as well, or you can download it ahead of time and follow along as I go through it.
No, so I'm also in the process of taking that sample project or a section of that sample project, and I've broken it out into a series of slides, okay? Just so that you can understand what each basic section of that code does and what you need to do to successfully load a sample project and get it running. So once that's completed, I just needed a few more screen captures for it. I didn't get them done yesterday. We'll post that as well, but it'll basically just be a short form of what's covered in the training video to be able to look at that and to put things together. Okay, so you can have a check with that. Please make sure to reiterate what James says is the first time that you do that build, you must be connected to the internet, okay, so that you can cache everything. Otherwise, you will get a build failure. Okay, so so that's very, very important. But then once it is cached, everything is there, so you should be all good to go.
Yeah, we've been getting a lot of issues of people that are not connected to the internet when they do a build for the first time. And the way that Gradle and this project and framework works is that it caches all the libraries once they're fresh in there. You never have to make any changes, and then you can go offline. But until that initial cache has happened, you need to be online for that build. If there's any updates we do for the VS Code library or a different vendor library, or you're updating from or creating a new project, you need to be online for that cache to happen. Anything else?
No, I think that's it. So we got about 9:14. We're going to stay online. If you want to try to get your software loaded and set up, right, do that, and we'll be here. Continue wiring your robot, and we'll be here. And probably in about a half an hour, we'll do a quick summary, right, and then we'll go from there and get you all set up for the big programming day on Thursday. Okay. Go find some money.
Okay, guys, I'm going to stay in the chat for till about 9:30, and then I'm going to end the call if there are any questions relating to the wiring or bringing a project into VS Code. Okay. Hi everyone, I had a question to show where the sensors will be going on the robot. It's not included in the CAD because I hadn't gotten to it yet, and it's not currently on this robot. But you have the different sensor mounts, such as the sharp sensor, and the ultrasonic sensor. These mounts allow you to put it on different areas of your robot, different angles, however you like. Essentially, there are 4 distance sensors in your kit. This should be used so that you can have, you want one of each sensor, or at least one sensor on each side of your robot. This gives you your distance from all 4 areas so you can line up your robot. It's up to you which sensor to use where. For example, if you wanted your ultrasonic sensor, you can mount it at the back here like this. The wires are in the way, but it can mount there. Then you'd have your distance sensor for the back of your robot. I can mount my sharp to the front of the robot here. It's up to you. There are a lot of, it's not going to mount directly like this. You're going to have to get some other parts like an inside L bracket or something to create it so that it will sit like that. Then there is the line sensor itself, so the Cobra sensor. It's not on here currently, but what I was using was the 48 millimeter standoffs that sit underneath here. That'll put the sensor a bit high off the ground, but we can calibrate for that with the, because it's analog, the different values between the light and the dark. Of course, you can also offset it a bit using some standoffs to push it even closer to the ground. So I'd have the Cobra sensor here in the front where it's nice and close to the object management system. I might have a sharp sensor that I also put here so I could track how close I am to the object. I might actually put that pretty close to where the Cobra sensor is. This would allow me to see how close my object management system is to the actual object that it'd be picking up. I would have a pinch sensor definitely attached to the one side of the robot for creating the square. Same thing on the other side here. I'd probably put one here too. That way I can give my left and right distances from a wall, and then probably use the other sharp sensor on the back of the robot for measuring the distance that I might be reversing into something. And that's why we provide 4 distance sensors in the kit, is that you'll be able to tell distance on all 4 sides of the robot.
Mm-hmm.
And then there are the limit switches. We didn't put the limit switches in the kit as we always allow people the option of doing it themselves or putting it in. But for this robot, what I would do with the limit switches is it would be used for the elevator, for the up and down. And I would tie it, because we're using an actual DC motor for driving the elevator up and down. Let's show better here. Because we're actually using a DC motor for it to go up and down. And because the Titan has built-in limit switch control, that if you hit the lower limit switch, it then disables the motor in that direction. So I put a limit switch at the bottom and a limit switch at the top of the elevator's movement area, so that when it makes contact with that switch, it will disable it in that direction, and it will also disable it in the upper direction. This enables me to not having to actually program anything because it's done. And we showed a way of doing that back in our elevator workshop, which is also on our YouTube if you want to look at it. The switches don't mount perfectly to the channel, so you might have to create your own 3D printed bracket for it to work well. And hopefully that answers your question on wiring the sensors. It's mostly just up to you, however you wanted to mount it for your control algorithm that you wanted to use. All right, everyone. Just wanted to say bye for the day. It's probably a good night for most of you. And we'll see you all on Thursday where we will be going over the programming of this. We'll be doing some autonomous so that you'll be able to see how to move the robot in autonomous. And if you're on the Discord, I posted a little teaser where we use PID to drive the robot 1 meter forward. And we're also using another PID, so we're combining PIDs on the different axes of the robot to keep it in a straight line while it's driving forward. All right, see you guys. Derek doesn't want to say bye because he's a grumpy old man.
See you Thursday.
Bye, everyone.